Have you ever looked across the top of a hot barbecue grill and noticed that wavy, shimmering distortion in the air? That optical illusion is actually a real, physical process called natural convection. Think of it as an invisible river of air. As the grill heats up the air right next to it, that air gets lighter and rises, carrying the heat away and pulling cooler air in to take its place. For engineers, knowing exactly how fast this invisible river flows is vital. If they can't predict how quickly heat will escape from high-temperature electronics, like the chips inside your computer, those components will overheat and fail. The catch is that the speed of that heat transfer depends entirely on the physical shape and position of the hot object. The surface itself acts as the terrain that this river has to navigate. To predict this, engineers use two main metrics. First is the Nusselt number, a scorecard measuring how effectively heat leaves the surface. Second is the Rayleigh number, measuring the fluid flow's strength pushing that heat along. By calculating these two numbers, engineers map out the flow of these invisible rivers. It allows them to predict exactly how a system will handle heat before a prototype is ever built. Let's look at the easiest path for our invisible river, a hot, vertical flat wall. Because hot air naturally wants to rise, a straight vertical surface acts like a wide open highway, letting the heat flow smoothly upward without any roadblocks. This slide shows the most reliable tool for calculating this vertical path. It is highly recommended because it stays accurate across a massive range of flow strengths, especially when the rising current is powerful and turbulent. However, there is a complication. Sometimes a surface isn't at one steady temperature, but instead pumps out a constant stream of heat energy. When that happens, the actual temperature along the wall varies from bottom to top, making the math harder to pin down. Here is the clever workaround. Since the temperature changes as you move up the plate, engineers anchor their math by measuring the temperature exactly at the halfway mark. This midpoint gives them a reliable average for the whole surface. Now imagine we tilt that open highway. If the wall is angled backward like a ramp, the rising air pushes against the plate, forcing the invisible river to slow down. This diagram shows the fix. The math accounts for that tilt by reducing the calculated effect of gravity based on how steep the slope is. It is like how a ball rolls slower down a gentle hill than a vertical drop. Whether the wall is straight up or slightly tilted, the core idea is the same. The math is simply measuring the speed of an upward-moving current that has a clear path to escape. This diagram shows what happens when the terrain is a flat, horizontal surface facing upwards. The hot air isn't sliding up a wall anymore. It lifts straight off the surface into the cooler air above, rising freely like a geyser. But if you flip that exact hot plate so it faces downward, everything changes. The hot air tries to rise, but hits the plate itself. It creates a thermal traffic jam where heat gets trapped against the ceiling, escaping slowly only around the edges. This slide shows how engineers measure these horizontal traps. They use a special scale based on the surface area compared to the length of its outside edge, telling them how far the hot air travels before breaking free. The terrain gets trickier when the surface is curved. Imagine an invisible river flowing over a hot, horizontal pipe. This figure maps flow around the pipe. Fresh, cool air hits the bottom, where heat transfer is highest. As air wraps around the sides, it heats up and becomes less effective, breaking off at the top to form a rising plume. This leads to a question. If you stand that pipe straight up, making it a vertical cylinder, does the flowing air still wrap around it, or can we treat it like a flat wall? There is a specific rule for this. If the cylinder is wide enough, the flowing air does not register the curve. As long as the diameter is large enough compared to the height, engineers can take a shortcut and treat the curved pipe exactly like a flat wall. These traps and boulders show that while the object's temperature sets the heat in motion, its physical shape and position determine if that heat can actually escape. So how do engineers keep all these rules straight? They follow a simple 3-step mental checklist to solve these problems without guessing. Step 1. Identify the terrain. They look at the component and determine if the surface is flat, round, standing straight up, or lying flat. Step 2. Check for traps. They analyze the orientation to see if the hot air has a clear path upward, or if the shape blocks the flow. Step 3. Pick the right tool. Once they know the shape, they select the correct formula to score the heat transfer, making sure to adjust for things like midpoint temperatures or wide cylinders. While the formulas look complex on paper, they are really just precise descriptions of that wavy, shimmering air about the grill, something you have seen your entire life. By studying the terrain and calculating the flow, we map out these invisible rivers, and by understanding exactly how they move, we gain the ability to safely control heat and protect the technology we rely on every day.